Welcome to a tutorial on deep learning. I am Animesh. I am third year PhD student working under Professor Menman. And this is my...
I'm Muthu. I'm a fourth year, about to graduate PhD student working with Professor Menman. Animesh works on deep learning, on information extraction, and I work on education technology, specifically books.
So without any delay, we will start. So first of important question that most of people ask that what is deep learning and how is it different from the traditional machine learning which has been around there for so many years. So the idea is that deep learning is the set of methods, technologies, algorithms which help to identify and basically do machine learning, basically only using the data, basically doing the feature engineering, but identifying the higher abstractions of data from the data itself. So deep learning is like a complete different set of domain, just in terms of different type of algorithm. But essentially the basics of machine learning still holds. Now in machine learning, we have three kinds of divided, vaguely we have three kinds of paradigms. So supervised learning, where we have labels and we want to predict something. Unsupervised, where we don't have labels and we still want to get some insight from the data. And then there is reinforcement learning, where we have some actions, and with each action we associate some reward or some penalty, and then we want to identify the optimal set of actions by which actually optimizes the rewards and reduces the penalty. So we can think of a lot of examples. For supervised learning, any classification based on label data. For example, classifying a spam versus non-spam based on the clicks made by user on the interface of the web app. And unsupervised, all kind of clustering, where you don't have any label, you just want to cluster people by age or by gender or by any other means. Based on some feature, you want to cluster them to form some meaningful groups so that you can make some insight out of it. Okay. So that was what kind of paradigms are there, but what kinds of problems are there? Usually in machine learning, there are few kind of, most of the problem can be two kinds of modeling. For example, either you would be taking some set of features and you will be predicting some value, which is essentially kind of one-to-one prediction or one-to-one learning. Then there are problems where you will having features and then you have to predict a sequence. So example of these kind of problem would be when you have to do for a picture. Suppose you want to generate a caption for an image, but you have to generate a set of tokens which should give some meaning out of it. Then many-to-one, ideal example would be sentiment analysis, because in text you have a lot of tokens and you want to identify one sentiment for the whole set of tokens. Many-to-many example would be translation, machine translation, because you have a set of tokens and then you have to convert into a different set of tokens. So in many-to-many, you will see two kind of formulation they have in the image. Basically, the idea is it might happen that in many-to-many formulation, for example, in machine translation, you might not have a direct translated token to one token, but instead you have a translated token for a group of tokens. So some of the token might go null and some of token might not be there at all. Many-to-many kind of modeling where you essentially have to output label for each of the token. For example, tagging. Moving forward, where do we apply these things? We apply the basic machine learning to almost all domains, like where we want to make some insights out of data given label. So NLP, you have the raw text. It's a artificial signal, and we want to identify some insight out of it. For example, real signals like what was the emotion content of that. Then there are some natural signals, for example, the image or speech, the frequencies, the different formats of frequency, and then we want to identify the information content in them. For example, what was inside the image? Was there a horse? Was there a... There is speech. Similarly, we want to convert speech to text. Use other signals, for example, the haptic signals, or it can be multimodal signals used by robots to identify what kind of stimuli they perceive. So These are all the various applications of machine learning based, which in last few years have found great advancement due to deep learning, because for each of them we will go and find a particular set of features and we'll say, hey, you know what, if you use these features, your algorithm will work. But in last few years, what we have been able to do is identify some higher level of abstraction, which we will see what those are as we go through the tutorial. And that has helped us to really achieve much higher strides in all these fields. So how is this promise of deep learning come to this decade, and why is it so popular? So basically, there are many things, high computational power, but other things being availability of data. We now have a lot of data. Like for every application, there is either public source or there are private people collecting data, and that has helped the cause of deep learning a lot. Other things is, as things, there are a lot of private and public players which have developed a lot of toolkits which need to make different kind of models. And given a huge amount of data and ease to make different kind of models, there has been a lot of enthusiasm in people to try different kind of model and see how it works. And most of the time, most of the model works. So enough computing power, huge amount of data, and flexible models has really helped the to move forward. We'll discuss about the deep learning reduces the curse of dimensionality. Just to give you a quick example, suppose you want to do image classification and you want to learn what different, ideally this was the way how people used to do vision previously. They used to identify what kind of features will help. So they used to say, you know, there is an edge in a particular direction, there is so different kind of edges, a combination of edges. Similarly, so what happens is, this creates a problem of having huge dimension of data, even at the upper level of abstraction. So moving, which is essentially something like, suppose you have to identify who is in the image, and you identify, okay, let's put a feature for gender, let's put a feature for there being a class, or let's put feature for all the possible kind of edges. Let's put feature that there's hair on his head or something like that. Now what happens is, in traditional machine learning, when you try to identify the feature at upper level of abstraction out of these features, it essentially becomes a lot of features. How do I want to put it? So suppose you have n number of units in the first layer, which are the n initial features which you identified. Then the next layer, it becomes n to the power d, because you have different combination of features. And what happens is, n times k features, which is where k is the upper level of abstraction, together produce a much abstract level of representation, which even a well-engineered human feature were not able to produce. Human feature, we identified that we will use these k features. Still, they were not able to produce those level of abstraction of features which deep learning is able to produce just by using natural representation of data, by not using human engineered. So this diagram again essentially represents the same thing, that initially people, first they used to have hand designed basically rules like, oh, if this happens, then this is this. Oh, if the hair is long, then the person is female, or something like that. And then they have these features to these rules to identify some other features, and then use those for output. Then some other higher level feature. Learning is happening is essentially the representation learning and deep learning. Representation learning identifies the abstract representation, which can be used as multiple layers to use in deep learning. What happens in deep learning is, essentially, we don't have rules. The natural representation of the data, and then we identify all the complex features from it on its own. When we progress through the tutorial, we'll see that how some of the abstract features were identified just from the pixels value of the image. So this is one of the research paper where the author tried to identify what is the place which is presented in the image. And when they try to identify that what does the neural network learns by identifying the layer the activation, the value of activation for the layers, they identify that actually it doesn't learn directly that what the place is. Some abstract feature that if there are maybe couch, then it's a hall. If there are field, there's grass, then maybe it's field. So these kind of abstraction, which ideally we would have coded manually, was able to identify on its own. So again, a lot of data, and we know that most of the natural data is produced by some natural distribution itself, and model tries to learn that distribution rather than we hand picking the features which we think will most probably represent the distribution. So before we move next to some math, okay, so because we have a mixed audience here, there is some math, but we need not go drill down into the math, but we still need to understand what is happening. So before we go there, we'll just show this representation, which essentially tells, it's essentially for beginners, but we'll just use it to some of the concept. So suppose you want to classify a simple data where we have some positive and negative samples. And what we can do is with basic feature x1 and x2. So this is a two-dimensional data. If you see, this is the original data, two-dimensional data. The blue represents positive and yellow represents negative data. So we want to classify this into two groups. So what we do is, let's start with one hidden layer. One hidden layer, let's remove more neurons. It's not working. Anyway, so suppose you have 4 neurons and we want to classify this data. So first of all, there's a common concept is randomly initialize the weight space. So just assume that what we want to see after the classification is that even for a random data, suppose there is a random data which occurs at this point, then ideally we want it to be assigned this label. So we want to see that the weight space, which is this, being orange here and the weight space being blue here, because we don't know what the actual data would lie, but we assume that this hyperdimension is the data is represented need to be partitioned such that it represents the most simplest form of representation for these two classes, but not any complex than the already available data. So if you start training, you will see what happens is it's essentially what a linear regression does. It tries to fit it, but here actually it's trying to change this boundary by learning the weight at these two, these four. And now what you can see is what is the weight contribution of each of the neuron. You can also see that intermediate neurons, which are these, are learning some representation. And you can totally tell that these neurons will have a very high weight to the final representation because these neurons have learned an abstract representation that it seems like I can check here. It just says live now. I'm not really sure. Okay, so you can see that there is a high contribution from this hidden neuron to the final output layer because this neuron is kind of learning the representation of the data which actually we are trying to learn at finally, which need to be transported to next layer. While these neurons are not learning that great representation of data, means that great the distribution boundary, so they have less weight. If you give let's change this to x2 square. Now this is interesting. If we change it to x1 square and x2 square and we run it, actually ideally this model wouldn't converge at all, because from x1 square and x2 square point of view in the data, because the data is actually, let me show you, it's negative here, and here it's positive, here it's negative, 0 to 5. X1 square and x2 square both will be positive. If it's positive, both will be positive if it's negative. So there's no such important distribution that can be learned to distribute the data. Most close, which is actually hyperbolic like structure in this this, even if you rotate this in any form, it can't represent a representation of data like this, because the diametrically opposite poles will be blue. So what I want to say with this is, with neural networks, you give the complete basic representation of data. You don't do extra bit of human engineering, and you will get good results. But if it's true with most of the machine learning algorithm that along with the basic representation, if you give some additional representation, it converges better, which happens here as well. So if you use the x1 and x2 and then rerun it, let's see what happens. We have introduced some nonlinearity in the feature. Though nonlinearity is available in the neurons due to the sigmoid function, you see it kinds of learn a complex boundary. We are not very sure that that boundary is true or not. Good kind of non-linear boundary. So even if you increase data to be more complex, like this, linear boundary does better. So the initial distortion is the initial way with what it starts, but the non-linear boundary can represent better decision boundaries, non-linear features. Coming back to where is this? Yeah. So next, the thing which changed the game of deep learning, basically, the AI winter was stopped because of this invention, is essentially the backprop. So what does so first of all, why you want to introduce the backprop is, this is the basic learning algorithm which is used by almost all of the deep learning models to update the parameter value to identify the optimal set of parameters such that we can predict the correct values. So what happens in gradient? So backpropagation is essentially a gradient descent, but what happens is we assign the value of error to that particular component, how much it is responsible for the error produced at the top layer. So how do you want to put it is, suppose we want to classify some X points into Y labels, and there is, then essentially there is a cost function which we want to optimize. Most of the time the cost function is either square error or cost entropy. So suppose we have a square error cost function, which is essentially predicted value minus true value square, or true value minus predicted value square. And then update. So for each, initially when we started the program, we had random distribution of weight of error. If you see, there was a small plot in the side which was showing constantly decreasing error. What happens in each iteration is we try to update the weight such that we decrease the error. We'll skip the math. Essentially what this math is saying is, just we get quickly there. Differentiate, if you want to get the gradient, what is the contribution of the error from this layer? What essentially we are going to do is differentiate the cost with respect to this layer, going to do is redifferentiate this layer, whatever we get contribution at each of the component at this layer, with respect to this layer, what is the cost of, what is the component of error which has been introduced by this layer. So this differentiation is partial differentiation. That means it only consider the contribution given by that particular index. So again, the same thing which we discussed, we have square error, and this is the activation, which we will see later and we will discuss as well. And this is essentially the model which we are discussing. A linear model essentially takes the input, multiply with the weight matrix, and use a bias and just that level. And then this is the loss, which is essentially cost of all the errors, which is, and this is the set of parameters. Each weight and each bias is at all the layers. Just leave it. Now, some very practical aspects. So we'll see that there are there is a whole jungle of non-linearities available to use in your neural network. Later, as we progress, we will see what kind of non-linearities are good for what kind of data, or what kind of non-linearities are generally used by people for certain purposes. For example, here we used a form of nonlinearity that is rectilinear unit. It gives from 0 to x value 0, and from x to anything value x. So again, here we use the square error for loss, but usually cross entropy is calculated from most of the NLP or most of the functions where we use a natural distribution to represent the data. We'll see why. And stochastic gradient descent, again, usually stochastic gradient descent gives the best result, even though it's a bad gradient descent. So we'll also learn about that. And samples, which is very important, because again, we will see why it's important in later part as well. Normalize the input variable, again we'll see. So basically we'll see most of these things, which are generally wisdom of the deep learning community, that these things should be performed on the data or just performed on the model to get good results. Okay. So now coming back to the learning abstract representations. So as we discussed earlier, that the earlier methods, the traditional method for vision where that people used to have feature extractor. Oh, is there an edge? Is there a circular thing which might be a wheel? And then they used to use train classifier directly on top of those external features. And then very recently there were features, and there were some combination of features to produce some mid-level features. But what happened with deep learning is you don't need to identify all the initial feature, all the mid-level feature, all the more complex feature, which will be combination of these mid-level feature. But what you need to give is just give the basic representation of data, and it will automatically identify the mid-level, high-level features, and it will try to learn whatever the classified it's supposed to do based on the loss. Everything is guided by the loss. We discussed already where most of the time we use normalization. Filter bank is a kind of feature which is generally used in vision as well as in speech. It's essentially aggregated sum of all the data point of a particular frequency in one band. So like this thing, the identification of abstract feature so basically later, which turned out to be one of the pioneering work in vision, the convolutional neural net. So initially they applied this work where they were trying to classify the MNIST data. Previously the error were more than 20, the error were around 10%, but then later it came down to 5%, and later now it's 2%. MNIST is now 99 something, 99.9, but this was the pioneering work which changed, which decreased the error by a lot. So what they were trying to do is they were trying to identify different F-bank features, and based on those F-bank features, they were trying to pool, we'll see what this, and then from these layers, they were getting some abstract representation here, and then they were trying to identify which of the values essentially it would be. So if you see MNIST data is very simple. It's actually a 16 cross 16 pixel image, and then there is a small word written over it, and then you are trying to identify what is 0 to 9, and you are trying to identify which of those characters it is. Fairly simple rule-based system can also perform this task. If you have rules like if there is circle, and if there is straight line, probably it's 9. If there is only circle, then it's 0, something like that. Later they improve the architecture, they remove the FBank completely. FBank is still considered to be a high-level feature, which is essentially made by humans. And later they change it to just the pixel value at that component. So this is the 32 cross 32 input, and this is the pixel value. And then they have a small convolution kernel going over this and generating some abstract representation, then doing pooling, and then finally predicting the value. Okay. The next step, moving from identifying the characters to identifying the handwriting, essentially which was done by using the same thing, but instead of doing a convolution in this way, which was done, oh, sorry. This is the standard part which we saw earlier for a character recognition. And along with this part, they have a linear convolution going over like this. So essentially, at some portion, they will output one of the characters, and then they will move forward, they will output another character, and they will keep doing this. So essentially, it's extending the previous architecture to one more direction. Essentially, that's a good thing about convolution, that it can be applied to 1 dimension, 2 dimension, 3 dimension. So it can one-dimensional linear data like text, 2-dimensional data like image, or 3-dimensional data like videos. Okay, so now the thing we were discussing earlier that actually tries to identify the abstract feature on its own. So what happens by using convolution layer, which are 2 or 3 or 4 layers deep, is at the first level, it tried to identify different edges, which were actually already using these as features, and they were having this different kind of Gabor filter in different orientation to identify what edge is in particular direction, because a Gabor filter in particular direction will try to identify an edge in that direction. This was already there. Then what happened is these were much abstract feature which people at some later point, but still these are very difficult to identify from human point of view. Actually, second layer, just I'll try to identify curves. So from first layer edges, second layer we move to curves. That's still okay, still human interpretable. What happened is at very third layer of using a CNN, there were much abstract feature like, or this is like a swan or something, and this is some wheel. So these things are impossible for human to encode. So in using CNN, you can always add multiple layers, and you can always get a better abstract representation if it is by data for that particular classification task. But by human encoding, you can only go to probably 2 layers, and that's all. So this to some extent explains the power of neural networks to generate the abstract representation, which is helpful for classifying that particular kind of data, and hence it's more powerful. The things which we discussed earlier. Okay, so what are the things the CNNs are good for? Anything that is space. So that is exactly why it works very well on image object identification inside image. Because what might happen, even if you train on corpus of image of cat by using some standard technique, if the cat comes at different location in the picture, it would be very difficult to identify. But because in CNN we saw that there is identification is done by a small convolution filter moving over the image like this, and then generating some abstract feature. So even if the cat appears here in the image, or here in the image, here in the image, it might fall into one of the convolution filter, and it might get into an abstract some feature here, which might get here, here, or somewhere, and then it would be classified. So convolution. So same thing applies to text. There is very promising result for text classification by using convolutional neural network, which again, the same group which produced for image published. What they are doing is they are using CNN for text classification, because we know that certain words, which are like high emotion words, they appear anywhere in the sentence, it doesn't matter. They convey the most meaning. This movie is terrible. Now then you can say a lot of good stuff about the movie, but probably the terror is the important word. So when you want to generate a representation which is independent of the position, go to use CNN. There is one more architecture which is very widely used, especially in text, and it also deals with linear data, and it tries to identify of sequential data is recurrent neural network. So what happens is, for sequential data, a data at a particular instance is dependent on all the data in the past, ideally, but because of high computational cost, we assume Markov assumption, and we'll say, you know what, if we know just the closure past, we don't need to remember everything from the start. So is solved by neural network, essentially tried to solve, but we'll see, by using a recurrent neural network. So what it does is, you have a sequence of token. Let's say you have a sequence of token from x1 to xt, and you want to predict some value at the tth time instance, suppose st, which is the output. So you say that it is function of everything which it has seen till that point. And what it is going to do is, it is going to predict for each time instance something, and then it's going to feed that output to the next step as well. So what we are going to take at each time step to predict output is that time step input, the token at that time step, as whatever was predicted at the last token. We're going to use output of the t-1th step, and then the current token at the tth step to predict at. So you can see how it translates to, you are dependent on every data, because the fifth data is dependent on fourth, and fourth is dependent on 3. So at each level of getting an abstraction from all the data previously it has seen. But world is not that ideal. So what happens is, when we calculate gradient, which comes back to which we are discussing, calculating gradient from a simple, which is the loss, and then we differentiate the loss with respect to each of the weights, and then we get the update for each of the weight. What happens in a recurrent neural network is, this is the output we want to get error calculated for. We differentiate with respect to this parameter, we get some error, but this as well. Now we go here, we differentiate this with respect to x and with respect to this weight parameter, we get some error here, we keep going the sequence. Now the problem is this: suppose the sequence is very long, and these weights are actually shared parameters, because you don't know how many tokens there are going to be. You always use the same weight for each of the token to do the prediction. Update for weight was very simple. Whatever error is introduced by that weight with learning times, negative of learning times. But this is difficult, because as well as here, as well as here, as well as here. So we can add all the weights. It goes back in time. The contribution of that weight towards the error decreases significantly. So what turns out is, when you add everything, you get essentially 0 values if the sequence is very long. Essentially, if the sequence is long and if your gradient are decreasing subsequently. If your gradient are increasing, then it will keep increasing and you'll get a very high value for the weight. And basically both way Either your network will not learn anything because there won't be enough gradient, or basically network will not understand there is enough contribution from the weight, or your network will learn something which is not even there. It will just catastrophically get to very high values and predict errors. This is essentially what happens. You have to differentiate. The overall loss with respect to this state is actually the product of each of the individual losses. And then what happens is, which obviously it will have get to, because if the sequence is very long, at least there would be at the end some value which will have very low contribution, because product everything will go to zero. So essentially, though we are saying that we can learn till from the first data to the current data what was the contribution, we won't be able to do that because of this problem. So there are a lot of tricks. So lately people introduced this. RNN has been around from 80s, but still it wasn't that popular until now. So people, during all these years, people have introduced a lot of fixes to solve this. This one is the most, I mean, my personal most interesting one. I think most of people use this one. Using clipping gradients, this is basic, that you don't want the gradient to be greater than a certain value, because if it's bigger than a certain value and it keeps propagating, you might get a basically exploding gradient, which is represented in one of the paper by you. I think Yoshua Benjo, it says that if you are moving, usually happens in LSTM, there are very steep surfaces like this. So in this hyperdimensional space, you are trying to identify the current, the optimal weight, which is supposedly say this is the global. You are trying to reach there in the weight space, and then you start from here. You are moving slow. This is fine. You keep on moving. You come here, but it might initialize from here, and you are moving like this. And then you make a small update, but because this is a steep surface, you reach somewhere here. And then the next jump you made, you go back at some very high place. So your gradient keep on exploding to very higher values, and very good. Basically, your network will not learn anything. So fix for this is to clip the gradient, don't use very high gradient values. Which is essentially like which is, as they say in their paper, is human neurons, that we lose some of the information. So leaky integration is, as the time passes, it removes some of the information from the neuron. And then there is momentum. This is used even in feed-forward networks. It essentially remembers the history of gradient descent. And even if in the current step a gradient is calculated, which we'll see why this is important, mainly in the saddle point cases. But in the cases where the gradient even is still not high, this helps to get out from the saddle point cases. With random values rather than initializing with extreme values. Gradient propagation regularizers, there are many. So LSTM we'll discuss quickly. What LSTM does is, in addition to the standard used by that particular step, the cells are called memory cells, input cell, output cell. Essentially what it's trying to do is another path on which the differentiation can go to zero. And they don't care about it, because most of the data which is coming from error contribution that data is making to the final loss is contributed by a different path, and they produce an additional path on which the error might go zero, and still the model learns. So LSTM is heavily used nowadays because, again, you see as in toolkits, it is available just by using a single direct command. And also it's very robust. So it doesn't have any of gradient exploding or vanishing problems. There is another version of LSTM which uses less gates, that means less parameters, and still produces good results, called gated recurrent units. Gates, which controls the amount of information which go into a LSTM cell, so that the sequential derivative doesn't become zero. Again, lot of math. We just want to go quickly on what are the general practices in so if you see this portion, this is essentially the weight rule, that we have a weight, we initialize with random weight, and we see that in each iteration, whatever is contribution of error with respect to the partial derivative to that weight, applied with the learning rate, is the weight such that it moves towards decreasing the error. So that's essentially the whole update thing. This happens for every part of the network, which is what we learned earlier. Sorry. So which we learned earlier to be backpropagation. So essentially the gradient descent toward all the layers is the backpropagation. So suppose this is result from one of the paper produced by the authors. I think Lee Kwan and other people. So what they say is the optimal learning rate for any configuration is this, which is the inverse second derivative of the error. But in practical, no one uses this. If you have learning rate smaller than this, much smaller, it's still okay. It will try to get to the local minima by making small strides by using this rule. At each iteration, it will try to decrease the error and it will try to reach the local minima. If you use optimal, actually that is what the optimal means. It will directly reach to the local minima, but no one does this. Identifying this is difficult. For most of functions, it's not. And this one, high value, it will oscillate. Because you are using higher value than this, so what you are doing is when you are updating, you are shooting to some value like here, which is here. So these values, these are the values of the weight. This is the weight value, and this is the error value. And value, then you might overshoot the curve and you might just keep increasing the error. Because once the weight has been updated to a higher value, the error which also increases, to correct the weight, the contribution of error is also higher. So weight keep on increasing, the contribution each step in the backpropagation keep on increasing till the weights keep shooting above. So we learn out of this that it's always good to use small learning rate. Purpose, people start between some learning rate of 0.01 to 0.0001, depending on how much data you have and how much is the model complexity, but not like not one, because those learning rates are very difficult for most of the model. Your model might not learn anything. So in case where you see the cross entropy is decreasing, you know that, oh, maybe the learning rate can be one of the culprits. Okay, so earlier we discussed about that we need to normalize the out. So essentially this is what the style is trying to say is, we are trying to predict an output which is, there are two x1, x2, and we are trying to produce an output which is w times xp, which is w times x1 plus w2 times x2. Which is essentially the same example which we saw. Find the boundary between these. And then here is curves for identifying that boundary. Okay, let's go through each of them one by one, which is essentially what we saw in the previous graph. If you use a small nmax is this, and you use a small learning rate, okay, so coming back, what will be the optimal for this is, for classification is, weight 1 and weight 2 both to be some value like here. Some positive values. I think this is positive and this is also positive. So weight 1 and weight 2, if both get positive value, then it's the global minima for this problem to classify these two lines. Slice from a random weight, which is here. And then in first iteration, it moves to this point, and then it keep on bouncing sides of the curve, and it tries to reach the local minima, which is global minima in this case as well. If you use a very high learning rate, which we saw earlier in the weight space, these wiggle should decrease and it should try to reach here, but instead the amplitude of derivative is small learning rate like this. Then what happens is you get it reaches there, but it takes no, it's relatively bigger than this one. So it's relatively bigger than this one. This one is relatively bigger, which I think is available on this side as well. Yeah, this one is relatively bigger, which corresponds to this case. Something around this case or this case, which is still okay. And the last one is this case, which we see as here. So which we see, it takes a lot of small steps to reach the place, which was not here. It was fairly reaching in few number of steps. So the point is, if you use a very small learning rate, it might take a lot of time to train, which is the obvious trade-off. Okay, now important thing, saddle points. So saddle points are minima with respect to one of the parameters, but it's not the minima. It might be maximum with respect to the other parameter. Most of the learning algorithm has this problem that they get stuck at the saddle point and then they never get out of it. The reason being that as we have learned from most of the machine learning classes, that most of the algorithms are called convex problems. So convex problems is where the local minima is also the global minima. The idea here is this, that using, which we saw earlier, things like momentum and other things. So using that, what happens is, here are two random starting point. It's a saddle, so it's like this curve, and then there is a curve here as well. So how do I want to put it? There's a curve like this, and there is a curve like this. So it's like this space, something like this. So the middle point is saddle point because the local minima is somewhere down here, but it's minima for this parameter. So these kind of backpropagation algorithm, they start with some random parameter. They keep wiggling. When they are about to reach the saddle points in some parameter space, they keep decreasing error slowly. And ultimately, when they reach the saddle point, due to the momentum or other things, they actually shoot out of the saddle point and they keep on going. And this happens for almost all saddle point. So basically what we learn out of this is, this assumption that the problem need to be convex to be solved by neural network is not necessary. Even if we don't know what kind of problem it is, it will reach to, and generally it's assumption that most of the problem when we are trying to identify such things, I think this is put in one of the paper as well, that local minima is an acceptable to the global minima. We can't identify global minima using any of these algorithms. Which we discussed earlier, rectilinear unit. Now I'll just quickly tell that why does rectilinear unit work better? And we also saw that the ImageNet, now if you see all the image related networks, whether it be AlexNet or GoogleNet, they all use rectilinear unit instead of sigmoid or tanh activation. That rectilinear unit have shown to a feature representation for the most important thing about rectilinear unit is it works even with less data, because rectilinear unit very quickly. Sorry, rectilinear unit doesn't saturate very quickly, unlike sigmoid and other values. So the upper bound of rectilinear unit is x. After a particular point, anything produce any output value, it outputs the exact same activation, unlike sigmoid, which saturates between 1 and -1. So this kind of unit works better because it tries to minimize the noise at the lower level of network. So if the values are this, it will just try to output. These network has shown greater improvement. One very famous technique which we always see and we'll even see later during some of the demos is dropout. This is one of the practical things. When the authors introduced the dropout, they were also in paper giving reasons which not a lot of other people in the community agree with, because it said that this method is from how our brain works. Some of the neuron fire, some of the neuron doesn't fire, but essentially it has it's kind of in a single model. What it does is, when you are training model, at different iteration, it tries to switch off some of the units, which would be totally random. So it tries to introduce some of the noise in the data or in some upper abstract representation of the data. So this way, when you use dropout, you are much less likely to overfit, because at each iteration you are seeing some new data which is having some noise with respect to the original data, and in this way you get much robust representation and an ensemble of a lot of classifiers which has been trained on different data altogether. Another practical thing to do is batch normalization. So in a stochastic gradient descent, what we are trying to do is we take one data point for that data point. Then we calculate derivative, which is the error with respect to each of the units, and then update all the unit. This might be very unstable because some data point can randomly produce a lot of error. And then you will update the weight with respect to that. So this way, though it gives better performance because it tries to learn from each individual data what is the error that each data point is. So it gives better result. The main problem is it's unstable. It's very difficult to get correct result with this. So what people do instead is take n number of samples together, n number of samples, divide that error by n, which is essentially the batch gradient descent. It's like this. So it's like taking average of n data points to calculate the error, which is robust because some of the data points even produce very random results. It's the majority which will produce better error, better predicted value, and hence better error estimation for the parameters to be updated. Another practical aspect which we use in neural network is early stopping. So what does early stopping mean is, we usually take a hand. After some iterations, we calculate error on held out set. We save that network. We keep training. And if in next iteration, whenever we check for that particular result again, if the error has not decreased, we discard. We keep training for certain number of iteration, but at the end, if still the error is not decreased, then we go back and pick that model. So essentially what we are trying to say is, we start with a random state, iteration, we test on some unseen data, and that unseen data is actually some part of the label data itself. So we know how much error, what is the actual label, and we know how much error it has produced. We log the error, we keep it. For next n iterations, then we check it again. It has decreased. Then we use this as the best model now, and we save this. Keep going unless until this happens. If this never happens after this point, then we discard all the models and we take the previous models. Early stopping. Basically, try to stop. We try to take the model which has known best result on unseen data. Hyperparameter. As we saw, all the weights and all the biases are the hyperparameters which need to be tuned, and all our whole learning is around getting the correct value of these parameters. Also saw that these parameters may affect the value of your final model, the prediction, extremely effect on the final prediction. Because if you start from some random position, you might end up in a different local minima. If you start at a different random position, you might end up at a different local minima. So what happens is, which is used is parameters randomly. Usually people use normal distribution because they assume that most of the natural things have normal distribution. So even so, suppose you want to slice 128 unit weight, 128 cross 128 or 128 cross uh, weight matrix, then you'll just sample a normal distribution and you slice with it. That's generally the best practice. So what is represented here is if you initialize uniformly, so these are two weights. Not an important parameter. So in this direction, you initialize anyway, you are not getting any error result. But this direction, you initialize uniformly, you might end up here. Initialize randomly all the different neurons, then there is a chance that you might end up having a local minima. So now that was all the theoretical aspects and all the practices in deep learning that people follow. Later we will use some of the live demo to show how those things are incorporated in the model. We don't need to mathematical formula there because everything is already done. We'll be using some modules like we showed earlier and referring back to whatever we learned throughout, that what part of the code is doing those things, and we'll see more how these things are implemented in the demo. Before giving, I will talk about how this has affected the speech domain. Till 2010, the performance of speech recognition was at the time where they were using HMM. HMM was introduced. I think Rabinov was the author. There was sharp decline in word error rate. And then if you remember from that time, when Microsoft has voice recognition from so many years, decrement in the error, static. Since 2010, when again deep learning came into picture, they saw sharp decline, and now the word error has approximately 10%, which is fairly good for production level systems. So this is the effect of deep learning on one of domain. It has similar effect on other domain as well, but that's one of the domain that has shown how things were static for a long time, and then there was breakthrough by deep learning. So now NLP and vision, then we will do the demo.
Okay. A key problem in natural language processing is finding good representations for words. Okay, words and higher level structures of words such as sentences and paragraphs and so forth. We have seen that the better the representations are, the better are the prediction algorithms and all the downstream applications. More than speech and image is affected by cascaded error rates in machine learning. Now, one of the very first applications that deep learning addressed in NLP was representation of words, also language modeling. Okay. In fact, the first application that was proposed by deep learning was not even a deep network. It was a very clever idea. What they tried to do was they tried to construct a vector space where the words could be embedded, and that would in fact represent the meaning of the word, okay, and that can be used in downstream applications, whatever be it, okay, be it summarization or be it machine translation or sentiment analysis, whatever be it. Okay, so when this is a very sexy result I'll tell you what they did. Before that, I'll tell you, I'll show you it is actually worth enough to learn what they did. Okay, now this has never been done in NLP before. I mean, there have been vector representations of words, but those vector representations were not computationally. I mean, you cannot do computational operations on those vectors, and the results won't represent anything. They were just simply some encodings to enable machine learning classifiers to understand that these are, and this can be differentiated from some other words through some form of distance. That distance did not represent any meaning, okay? Whereas this particular, if you see this particular example, the word representation, the vector representation for the word king and queen, distance, that when you subtract the vector for man and from women, the vectors were equal in magnitude. Okay, and similar kinds of operations were also possible with see. You can take the vector, the city of Paris, and subtract France from it, add Italy, and it will be closer to the vector for the city of Rome, right? Such an amazing representation for word vectors in terms of semantics was never seen before in any of the NLP models. Okay, we will do a short demo, and we will let you actually get your hands on this particular approach later in our tutorial. So, right, how did they actually do it? So this has only like 3 layers. Okay, there is an input layer, there is an output layer, and in between the input and output, you had one hidden layer. Okay? A really large, high-dimensional input and output layer, and a much smaller hidden layer. Now, they chose a word is generally known by a word's meaning is generally represented by its context. Okay, this hypothesis is called distributional semantics. Okay, and this is a very old concept in NLP, and it's very well known. So you take the vectors for the context words, and then try to print the target word. And while doing so, the representation that you learn by the hidden layer is what you are learning. Okay, and that is what is called as a word vector. Like most applications, you are not actually using the output layer's output for as in your downstream application in word vector. You are actually taking the hidden layer's output and you're using it for downstream application. Okay. Okay. So I have to quickly move on to the next second application that is very popular these days. An encoder-decoder framework. Encoder-decoder framework networks are very popular for machine translation, okay, and as well as abstract summarization. I think everyone is familiar with what a machine translation task is. Like you have a source language, you have target language, and machine is supposed to take in the vectors from the source language and output the target language. Summarization is it has to read one giant document or multiple documents, produce or generate a summary that has words or sentence structures that are completely different from what it saw in the source document. Okay, like summaries that are written by humans. Okay, this particular framework. So the second diagram that you see on the bottom half of the screen, it has an English encoder, English decoder. So such a setup might be useful for tasks, whereas the one on the left-hand side would be used for translation tasks. Okay, and there are like a lot of variants of this network. I'm not going to go to the mechanisms and variants of this particular network, but I'm just trying to give a very high-level picture of what kind of networks are popular and how you connect these networks with NLP tasks. so that you get an intuition of what type of tasks that you might have and which networks you could possibly choose. Okay, but the good part is the code base for these types of networks are all in open source. It's available on the GitHub. So the most popular, one of the really recent most popular libraries for this is called Seek to Seek by Facebook AI Research. So you just go to GitHub, search for APIR, and you get to their homepage, and you can just use it. Okay. Okay. So there is another aspect of that is very well known in the image community, but has found recent use in NLP community. It's called attention. Okay. Now, in tasks such as the sentiment analysis, right? Not all words are equally useful when trying to predict the sentiment polarity of a document. So in order to incorporate this intuition into the model, there are an additional set of weights called attention weights. So by which you can focus attention to certain words. So in a movie review, if somebody says the movie was terrible, and then blah 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 blah, you want to focus attention on to the word terrible and give a very high weightage to it, and that will tremendously help your classification, right? So from a mathematical perspective, attention is nothing but another set of weights, a set of parameters added to the zoo of parameters that deep learning has, another set of parameters that you need to learn by incorporating your training algorithm, and it turns out that is actually quite useful. In an image context, attention is used in a slightly different manner. So let's take this example of image to text, which the task is basically to have take an image for the particular image, right? So on the bottom of the screen, you see an image that is divided into grids. So attention would be something like what you see on the yellow bounding box here. The key part of your caption is going to consist of an object that is going to occur in this particular part, not on these portions of this image. So therefore, you come up with a vector, and that vector is going to it's going to be like a mask. Okay, so let's say there is a big matrix representation of this image, and this vector is going to be something, and this attention is going to be some sort of vector, and there is going to be some sort of matrix multiplication, and you get the output will have higher values than for this part of the matrix, and therefore it is helpful for you to generate a caption that has attention on this part of the image. Okay. Okay. So yeah. So this graphic represents how the attention is being applied, and these are actually the images that you see. The first image that you see is the source image, and the rest of the images are actually intermediate representations coming from the neural network. The spotlight actually shows you the attention, and you can see the word that is being correctly identified that corresponds to the spotlight. Okay, in the first image, frisbee, the underlined word, is where you get the attention, and you can see that the spotlight occurs on the attention over here, right? So here you see a pup, and it says dog, stop sign, trees. This is not a very good example, right? It says trees, but actually the attention should probably be on giraffe, I guess. I don't know. Let's look at some few of the bad examples as well. This is not a perfect technique, but yeah, here the image recognition is not great. This is a giraffe. It says bird. This is not a clock at all. So there's some T-shirt design. It identifies this as a clock. And this is identified as a skateboard, and funny things can happen. Okay. So another network, moving on. This is very recent innovation. Memory networks, again from Facebook research. So we already talked about memory, right? When Animesh introduced long short-term memory networks, LSTMs, of recurrent neural networks, we already talked about memory. So how is this memory different from LSTM? LSTM memory is actually encoded within the network. Okay. To have a layer, and and the layer has several neurons embedded within the neuron. Now this is an external memory. Okay. Think of how we read text. Okay. So this particular network, they performed very well on reading comprehension task. There's a long passage, and then there are a few questions, and the machine is supposed to identify, output answers. But these are factoid answers, like simple answers, yet it requires the machine to like understand the whole thing and like remember things from far back. Okay. When you use a long short-term memory network, it can't remember this far back. It would at most go up to like a couple of sentences far back, which is useful for an NLP task like co-reference resolution or name entity recognition. For this kind of task where you would actually need to go back and refer to things to actually answer. As humans, right? We have done this task in our high school, right? When we see the questions, we go back to the reading comprehension and read it again, and then we try to answer it, right? That means there is a need for additional memory, right? So that's what they tried to encode here. So they had a read operation and a write operation. They have an external memory. So they read and write, and so these networks are called mem, and some there are a lot of variants. Okay, so depending on the system, they go the corresponding parts from the memory back into the LSTM or whatever network you are combining with this memory network, and then they try to get the output. Okay, so again, you don't have to. If you are just looking for an application, you don't have to bother about how this is done. As open source library, just use it. Okay. Okay. Yeah. Another network that I just want to like skim through is autoencoders. Very different kind of network. These kinds of networks come under the generative types of networks. So what you do here is you have an input representation. An encoder produces an intermediate representation, and you try to reconstruct the original input from the encoded representation. Now, why you want to do this? Because this gives you an opportunity to actually calculate the error. So you have an input representation which is already known. Now you come up with a reconstructed input error between this and this, right? Why is this useful? This is because this is unsupervised learning. You don't need labeled data to do this. If for all other networks that we saw so far, like LSTM or blah blah variants of LSTM, you needed labels. Here in autoencoders, you just need to have a lot of data that are not labeled. You don't need annotation. This is a big plus when it comes to NLP. Okay, NLP requires tedious annotation, and unsupervised learning, you don't need any annotations. Okay. So basically, from the reconstruction error, you train the network more and more while you have representation to reconstruct the original output, and that you assume that the network has learned. Okay. Okay. Another variant is this one. This is like a really stuff that's going on in deep learning. In image community, in the past 2 years, there is this dialogue community where they try to generate dialogue from previous dialogues. Okay, to apply this is 2017 research. 17 February, Facebook has come up with this particular using generative adversarial networks. So the key idea here is this adversarial training. Okay, so you have two networks, and a discriminated network. A discriminated network is the actual network that you want to train. Okay, A generated network will generate some fake data, some training data. Let's say you have around 100 samples, but you want to train a network with just few hundreds of samples. Okay? So we'll try to produce an image of a cat, that something that looks like a cat but not actually a cat. But you have another image of a cat. Now the discriminator network needs to identify the difference between these two, and it needs to try and guess that this is fake and this is real. Now the output from whether the discriminator correctly identified the image or not is fed back to the generator from the discriminator, and generator thus improves its ability to produce fake images. So the next fake image that is coming from the generator will be better than the past fake image. So discriminator's job becomes more difficult, and therefore you are going to try and produce a better classifier over time. Okay. So this type of training paradigm is called adversarial training, and it is a state-of-the-art technique. A lot of tasks in NLP can benefit from it, because again you don't need a lot of training data if you follow this. But still, it's in infancy. Okay, mostly the groups that are applying these methods are not NLP groups at all. They are deep learning groups. Prominently, this is being pushed by Yoshua Benji's group at Mila, Montreal. Okay. This is an example. Okay, so we saw word representation, arithmetic operations on word representations, right? So this is on images. Actually produced by a deep learning network, believe it or not. Okay, so you can see a man wearing specs. There is a vector representation for a man wearing with specs, and there is a man without glasses. You subtract these two and you get and then add a woman with glasses, you get a vector representation for women with glasses. Actually able to produce, the network is actually able to generate this particular image from these three representations. Okay, right. Before you move on to the hands-on, let's just conclude the session on the big picture of deep learning and where we are headed. Okay, where has deep learning benefited a lot? It's the problem. The primary problem was we had a lot of data. Allowed us to take advantage of large amounts of data. The primary bottleneck was computational power. Previously, to take advantage of large numbers of data and to use neural networks to train or learn from them. That has been broken. To train neural networks in parallel, we have and neural networks have become more and more complicated. It has allowed us to come up with more complex architectures. Yeah, 20 years before, we could not even imagine that we could actually train something like an LSTM network. Okay, LSTM paper was actually published in 1997, but until very recently, we have not seen very complicated or deep LSTM networks that can do question answering type tasks. Okay. And that has been, at least for the NLP community, that has been it has been broken basically, right? In sequence typing tasks and in the machine translation tasks, you are no longer bounded by remember information that is bounded by these macro representations. Okay. Now, and as far as the image, speech, and those communities are concerned, higher level abstractions are extracted directly from lower level representations without any annotations. People don't have to encode. Annotations is one part, and the other part is people don't have to encode things that are known to humans from images or speech in the form of features. Okay, so if there are two or three things that you need to remember from this tutorial, is this. Okay, just move on to a hands-on session. I mean, if you want to try I mean, we will show a demo here. Okay, and then if you have a laptop and access, we are going to provide access to our lab server. You can log into it. You will need to be able to do SSH to the next server. If you can do it, I can just try some simple things like word to vec and stuff, just so that you feel gratified of coming to today. Animesh.
First we do the slides, then I don't think we have time. 5 minutes. No, okay. 5 minutes. It says- Nothing. You tell the instructions for login. So exactly. Yeah. How many of you here have SSNet, NUSNet IDs? Okay. Oh, good. And how many of you are from computing? I want you can sit with people who are not from computing so that they can also log in. So you know how this works, right?
Yeah.
Everyone has VPN, right?
You need SOC VPN to be able to SSH into our server. Everyone is familiar with those people are from computing. They are familiar with VPN, right? Yes.
Haven't used SOC VPN? I think you VPN is down.
Yeah, just go to this client. Show them.
Okay, you need to install Fortis. Think this client, Forti client, and then in using this anyone has that? NUS SOC VPN. You don't have. You still have the slides. You still can try it throughout the day. You will keep the accounts open so that you can try. Tell about the frameworks because people would want to use some of these things in some of the projects they want to do. So we'll just go through what are the most prominent frameworks which are used by research groups, and we'll give some quick small examples and how we run it. Okay, and then we'll refer back to whatever we learned earlier. What are different types of things: regularization, patch gradient descent, patch size, learning rates, and see how those parameters are fixed as switched in these models to do the learning. So in case people can't log in, so I'll just go. What has happened in last few years is, okay, this is training time on CPU. This is training time on these, okay, I think you can't see it. Both are Pascal from NVIDIA. So NVIDIA is the leading company in GPU. They are producing GTX, ITX, and all these GPUs are decreasing the training time. These are practical. These have been benchmarked by different people. So the numbers might vary, but they have been benchmarked by a lot of people on a lot of data sets. These are different data sets. I think this is ResNet, and this is so all these three are ResNet, but different versions. These are the bigger ones. So the training time hugely decreased if you use GPUs. So that's one of the prime reasons whenever we use, we have to train models. Some of the models might take weeks or days to train, and those models might just be trained in 1 or 2 days on GPU if you have huge data. So that's why we prefer using, this is the time, so we prefer using GPUs. Okay. The current scenario of different frameworks. There is Caffe, used by UC Berkeley, and then there is Caffe 2 for their production and their machine learning productions, and which goes in Facebook product. Torch is from Leekan's group. It was from initially NYU, but then as Leekan moved to Facebook, it went to Facebook, and now Facebook is also using this. So this is also very famous. Of all, this one, basically it came From Theano came from University of Montreal, Yosha Benjo group, and later Google introduced another framework, TensorFlow, which is actually very closely related to Theano, except for some optimization, some differences, but it's essentially a NumPy and SciPy based technique, which is it's a Python library, very close to this. Lua, Cafe is Lua. Then there is CNTK C++ based from Microsoft. I don't think it's that famous, but some people still use in speech and other communities. Paddle from Baidu, Net from Amazon, they use mostly for their own machine learning things. Basically, all the AWS services, when they provide, it's going through this. And there are many others. This one is the most interesting one because this is supported. This just came, not this year, last year actually in 2016. And far this has become the most used and most well-maintained because it's from Google. They use it in their production, they use it in their research, and they make all the code public. The good thing is that you can use all the Google code, which they come up with each of the conferences with. Okay. In all of these models, if you remember our first slide, something, I'll just go back quickly. Discuss that something like this. Why are we doing this? Just to calculate gradient descent. So actually the reason is not just only that, based on same modular approach. So the idea is this: network will have individual component. Actually, this linear component is nothing. It's just a weight matrix and it's a bias matrix. It's nothing. It's a function which just performs 0 to x. If from 0 to something to x, then 0, and then from x to onwards, it's max of x and that number. So the same thing, the same theoretical abstraction get translated into the code. And to the code, which is here. So we want to do this thing. We have two units, x and y. We want to multiply. Suppose this is the computational network we want. That is a complex computational network that has a big matrix feed forward to a CNN. Suppose we just want a simple computational network where we multiply two numbers. So these two numbers will be features. Suppose we will have some feature tuples as 1, 1, 1. And we think that the label is generated by this procedure. So we want to learn the parameters B such that we generate the label. That's goal in this network. So data X, Y, Z, for example, 1, 1, 2, 2, 3, 7, 7, 8, 9. And then there are labels like C. For 1, 1, 2, it's 4. For 2, 3, 7, it's 8. 9, it's 20. And we want to learn what is the function that produce this thing, which is essentially what neural network will be doing. Even in classification, we have sequenced thing, and we want to label it as 1 or 0. So suppose we identified that we assume that it is doing something this, and then an abstract representation added by, and then doing a summation. What we would be doing is we're using a NumPy array. This portion is common between TensorFlow, Theano, and all the framework. We'll just see why was there even a need for TensorFlow when the NumPy was already there. So what we are going to do is we will initialize an X NumPy array X, NumPy array Y, NumPy array Z, and then want whatever output we actually have the label for, and this is the process we assume that the network should learn, that X plus Y and then A plus Z to produce C. Okay. As discussed earlier, at each iteration, what we are going to do is upgrade all the parameters with the updates from the error it has made. So ideally, we want that after each iteration, A need to update it by A plus something is like this. Here in case X, Y, and Z need to upgrade it. So the problem is this calculation, this network, but suppose the network is an LSTM, then everything that we discussed, the whole Jacobian, the whole multiplication of different Jacobian, all the clipping, all the bash normalization, everything you will have to implement on your own. So this problem is solved by all these higher level frameworks. What they do is functions like tf.gradient, data point and output data point, and it will give you gradient with respect to all your parameters here, x, y, z. And then you can use these parameters to upgrade your initial, you can use these gradients to upgrade your parameters. So we are initializing it with a random variable in the session, and we are trying to run with these gradient. So let's move to next value, next graph. So this is same as NumPy creation by just, so NumPy is Python, so it's symbolically you can create, symbolically you can add and do operations on vectors, which would be essentially NumPy arrays. Here also, actually they are NumPy array, except for fact that NumPy array is a which get flushed out. These TF placeholders are static variables in the memory. That means once they occupy space in the GPU, they are going to be in the GPU for procedure, which is kind of necessary because there is where the lot of speed up come from, because you are going to use that training procedure a lot of time, a lot of iterations using the same data. So these placeholders keep all the, whatever goes in these placeholders are memory in the GPU, which are persistent. Is we create the symbolic graph, whatever this operation we want to do. And then we calculate the gradient. We initialize with some random value. And then we try to, session.run essentially tries to fit these values based on the C. Try to update with the gradient. So this thing is actually a function. Nothing is called here. It's just a function which will pass here in session.run so that it updates the parameter based on these gradients. Fairly difficult because you need to create network. Actually, you can create network easily, but you need to write the symbolic link for network. So there are higher level wrappers for essentially what we had planned to use demo for. Is one of most famous one is Keras. It's open source and also it has a lot of examples. What you can do is you can create a sequential model. By default, all models in Keras are sequential. This doesn't mean a sequential layer model. It means that model feeds in a sequential fashion, like feed forward or LSTM. So everything comes under this broad class of models called sequential in Keras. And then simple feed forward layer. So in this model, you can add a feed forward layer. Then you can add an activation, a feed forward layer. So this is exactly like what we saw in the theory slide, that it's essentially like you take X, you add a layer, it's basically a transform on top of that X, W times X plus B, and then whatever output come, you add another layer on top of this. So this is written just to emulate that thing, whatever we draw. So essentially you come up with a complex network, you draw it, and then you just use different components which are already existing, get that model. If you want to change one of the components, you might have to write a separate module, something like a dense layer. You might have to write my own dense and then use it. But essentially, the idea is most of the network which you want to create, you will get the basic component like dense, these things there. Now, you will need an optimizer like SGD. We saw there are other optimizers like okay, I can't recall now, but there are a lot of optimizers choice. For example, you can use Adams here, or yeah, you can use Adam, you can use SGD. There are some than SGD, you can use that as well. In you can compile with, we saw mean, we also talked about cross entropy error. You can combine with different kind of error. You can pass the optimizers, computing the error with that. And then you can fit using the labels and number of epochs. We also discussed about a lot of other things like early stopping and all these things are supported. For example, in this dense network, if you want to initialize this with random variables, you can use a parameter comma here equal to normal. That means it will initialize with some normal activation, or you can use L1 or L2 regularization on top of these layers. Similarly, you can use a lot of other stuff here like early stopping. You can create additional module here, stopping, and then you can use that. So these are the things that we discussed. Finally, you can dedicate resources, run this program on. Most of the time, you will want to run it on GPUs. Okay, so I'll just quickly show you how it I think it's already time. But okay, so what we can do is all the people who are in NUS undergrad, I mean, who have NUS Net ID, we already have these demo available. I think it still will be around for a few days in using these instructions, and you can run some of the demos and use some of the things we discussed earlier, like back normalization or early stopping, which are it's already in the examples, and see how it works. And that I don't think we have anything else. For NUS undergrad people, so to learn more about machine learning, then we are having this course this semester. Also, we are having deep learning vision, which is a community course, and deep learning for NLP. And this semester we are having deep learning for vision. So everyone is invited. It's an open course for NUS, non-NUS people, everyone. And not the least, the references. So everything is taken from NIP's deep learning tutorial. So there are a lot of other stuff as well, a lot of other mathematics as well. But we have tried to keep it minimal mathematics for wide range of audience we have. And also the tutorial for different frameworks. If you want to learn more about the framework and which framework you should be using, which framework is used in production and all those things, you can refer to Prof. Fepeli's 8th or 7th in CS231 and slide materials. So you can know about all the frameworks, how mostly TensorFlow and Keras, how to use those frameworks to construct basic graph, like we did in this these examples. So these have been taken from that place. So yeah, I think that's all. And questions? Okay, in case you have any question, you can send me, or we will be around.